Hello. In this video, we are going to prove the following theorem. Let G be a group and H be a non-empty subset of G. Suppose for all A and B in H, A times B is in H, and for all A and H, the inverse of A is in H. Then H is a subgroup of G. Now, before we get into the proof, let's first remind ourselves of some things. First of all, what does it mean for G to be a group? It means that G is equipped with a binary operation and satisfies the following properties. We have that G is closed under the binary operation. The associative law holds. There exists an element E in G, which we call the identity of G. It has the property that for all A in G, A times E is equal to A, which is equal to E times A. And lastly, every element of G has an inverse. Now the whole goal is to prove that H is a subgroup of G. And what that means is we want to show that H is a group under the same operation as G. In other words, we want to show that H is closed under the binary operation. We want to show the associative law holds for H. And we want to show that H has an identity element. And we want to show that every element of H has an inverse. Okay, so now let's get into proving this theorem. To start with the proof, let's first give ourselves a group G with identity element E. Let's let H be a non-empty subset of G. And let's suppose 1 and 2 hold. And from here, the whole goal is to show that H is a subgroup of G, which means we want to verify that these 4 conditions hold. Now first, we know that closure holds, because that's precisely what 1 tells us. So next, let's verify associativity. For associativity, we're trying to prove a statement about every 3 elements in H. So let's give ourselves 3 arbitrary elements of H. I'll call them A, B, and C. Now, since H is a subset of G, this tells us that A, B, and C all belong to G. But remember, associativity holds in G. So since A, B, and C all belong to G, we have that this equality holds. So we see, given any 3 elements of H, this equality holds. That tells us that associativity holds in H. So at this point, we verified the first 2 conditions. Now let's verify H has an identity element. Now, since H is non-empty, this means that H has at least 1 element in it. So we can choose some element in H. I'll call it P. Well then, by 2, since P is in H, that tells us that the inverse of P is in H. But then, by 1, since P is an element of H, and the inverse of P is an element of H, that tells us that P times the inverse of P is an element of H. But remember, since P is an element of H, that implies P is an element of G. So then, according to the fact involving inverses of elements in G, we know that P times the inverse of P is equal to the identity of G. So this tells us that the identity of G is an element of H. And so the claim is that the identity element of G is also going to be the identity element of H. And to verify that, let's take E prime to be E. From here, we want to show for all A and H, A times E is equal to A, which is equal to E times A. So since we're trying to prove a state about every element of H, let's give ourselves an arbitrary element of H. Call A. Now, since A is an element of H, certainly A is an element of G. But remember, the identity element of G tells us that this statement is true for every element of G. So we must have A times E is equal to A, which is equal to E times A. So this shows, given any element of H, we have that this equality is true. So this shows that E must be the identity element of H. So this verifies this condition. Finally, let's show that every element of H has an inverse. And to do that, since we're trying to prove a state about every element of H, let's give ourselves an arbitrary element of H, call it A. And the whole goal is to find an element in H with this property. Now, since A is an element of H, well then by 2, that implies the inverse of A is an element of H. And remember, this inverse element is the inverse that A has in G. But the claim is that the inverse that A has in G is also going to be the inverse that A has in H. So, taking B to be the inverse that A has in G, and at this point we've established that the identity element of H is the identity element of G, so I'm going to replace E prime with E. So from here, we want to show that A times the inverse of A is equal to E, which is equal to the inverse of A times A. And to show that, well, since A is an element of H, certainly A is an element of G. But then we know that this equality is true for every element in G, so in particular it must be true for A. And that's exactly what we wanted to show. So this shows that the inverse that A has in G must also be the inverse that A has in H. So that verifies the last condition. So this tells us that H satisfies all the requirements to be a subgroup of G, and therefore H is a subgroup of G. And so this completes the proof. And so yeah, that's pretty much it for this video.